Thank you. So I am a software developer at Jane Street. And just to give you a little bit of background about like what we do and why this kind of thing is interesting to us, we are a trading firm, and what that means is we trade stuff on exchanges. There's kind of like a huge important bit of this. In addition to like knowing how much things should cost and like being able to price things, you also have to just like be fast, because otherwise people might, like, we say pick you off, which means like just you have some orders out there and you can't react when things change fast enough, and you might be really, really sad if this happens. So we care a lot about our code being correct, because if it's not correct and is fast, that just means we will like burn money in a tight loop as fast as we can, which is obviously not great. But we also do care about the speed. So I'm going to talk about some of the like ways the OCaml type system has allowed us to satisfy both of these constraints. So I think like for the most part, like most of the coding we do, we kind of use a core subset of the OCaml language that is kind of like the typical type system that you're used to without any of the like weird fancy features. Like, you know, we care a lot about abstraction, we use that all over the place. We care a lot about like, you know, some types, we use those all over the place. But like, we don't use some of the fancier features most of the time. And it's partly because we don't need them, and partly because like the complexity has a cost. You have to understand it. However, in the case of some of these low-level like performance systems, it turns out that I think that the complexity of these language features is like far outweighs is far outweighed by the ability to like get a safe system, but while doing kind of dirty hacks. So I'm going to show you some examples of some things that we've done that I think are interesting. I'm going to show you a bunch of code. I'm going to try to explain it. Feel free to interrupt me and ask questions when I inevitably make the mistake of being unclear. To start with, one of the biggest, most important things we have to do is like send and receive messages to the people we're trading with. And so because we're trying to be fast, we need to like parse those messages as fast as possible. So what that amounts to is basically you read a packet off of the wire, and you kind of can't do anything else. You can't like copy it into memory. You definitely can't allocate like an OCaml object. You have to just leave it there and parse it in that buffer and like do every way in which you're going to react to that message. You need to do like without loading it into memory in any other way. And it just like turns out if you try to do anything else, you're just going to be slow and sad. So the reason allocation in particular is really bad is that it causes like latency spikes. When, in particular in OCaml, which is garbage collected, a garbage collector will run, and then suddenly like you have to wait a while. And this is really terrible. But also just, you know, the cost of doing this is higher than not doing it, so we prefer to not allocate when we don't have to. So I'm going to just go through an example of like what. Sure. Is this better? So I'm going to go over an example of like a protocol that I made up, and show you how like one might think to parse it and how we would actually parse it in practice. So a protocol could be like one of these 4 messages, and so an exchange could tell you like heartbeat, meaning like we're still not dead. They could tell you like here's a new order, which is like a new thing you might be able to trade against. They could tell you that an order went away, which means you can no longer trade against that order, or they could tell you that a trade happened. This is like pretty specific to what happens in finance, but like the point is there's these 4 messages, and they've got some like data on them. The data is different per message. You care about which is which, and you might write a parser that takes like a string buffer that it got over some network connection, and you might like write a parser that translates to this type. But that violates what I said about copying stuff and allocating. So we can't do that, but that would be like the simple thing to do. Yeah.
You're talking about network messages?
Yeah.
Over TCP or UDP?
Yeah, generally UDP multicast specifically.
So when you read message from the network, you have to store it in the buffer, right?
Yeah.
That is socket buffer.
Yep.
So that is allocated. You are saying it should not be allocated?
We don't allocate a new, well, certainly we don't allocate a new one every time. I'm saying like, you want like, your networking, so there's kind of a separate part of this, which is like, how do you actually read the message from the network? But at some point you have in memory some essentially string that you got from the network. And I'm saying you don't really want to do extra copying of that string after that point. In particular, we also use some like accelerated hardware stuff so that even getting it into memory is basically copy free. But that's kind of outside the scope of what we're talking about here. So what you might do is you might say, okay, well, instead of doing this nice thing, I will just like define, I'll just say, okay, I have some raw message type, or so raw type for messages. I'm just going to implement it as like, a buffer. This is like a type for a buffer in our libraries. And that's it. But like, this is kind of, what do I do with a buffer? Well, I can write a bunch of functions that like access that buffer and like get out the various fields that I would have had in my nice like variant over here. But like, this is kind of not great. Oh yeah, and so like, because it's still pretty easy if you just have a message to like, what if it was an order added message, but I just call like symbol on it, or like, this symbol function on it. That probably doesn't work. So you have to like maintain this discipline of like not accessing this raw buffer in the wrong way, which is pretty unpleasant, I think. A thing we've done is we've said, okay, instead of doing that, we'll use a JDT. So this actually, I think in practice, works out a lot better. So in case not everyone is familiar, sorry. I was about to say that. Yeah, so in case not everyone is familiar, there's a thing called, sure. So here's this part, which is what I'm about to explain. So in OCaml, and I think Haskell has this as well, there's a thing called a generalized algebraic data type. And basically what it is in addition to what you're used to, where you can create like a sum type with a bunch of cases, you can constrain the arguments to your type with like depending on the sum tag you're in. So like instead of just saying like heartbeat is a some message type, we specifically say it's like a heartbeat message type. So now what this gets us is if we match on a t with some type argument, in the heartbeat case, we will get that the type argument, we will learn that the type argument is equal to heartbeat. Yeah.
There should be something algebraic about generalized algebraic data type.
I think they're kind of, I mean, I'm going to say something controversial, which is like, I think they're kind of a generalization of the concept as it exists in programming languages and not really a great like theoretical generalization of the problem. I think theoretically they're basically, you take regular sum and product types, you add type equality constraints. So another way to think of this, is I could write of like, if I had some like equality type, it would be like, there's one extra argument, but it's like kind of implicit to this heartbeat constructor, which is like a proof that tick k equals heartbeat. And then when I match in the constructor, I get out that proof. So I now know that like my type argument was equal to heartbeat. So that's like a way of writing it in a more traditional like data type form. So yeah, and the other thing they add in addition to this is they add existential typing, because it turns out that like those two features are work really well together. The combination of things you can do when you have both of them is a lot more useful than if you only have one. And that's what's actually going on here. I'm just using the JDT syntax to create a very simple existential type, where I just like, this just means there's a constructor called t, it's the only constructor, and it just takes like a t and just hides the type. Right. Any questions about that? Yeah.
So how much control do you have over the format of these messages?
0.
So then you must be parsing something stored, and you must be applying. I mean, if it's coming as an Ethernet packet, right? And there's something going on here. You are telling me what should be the format, what format you would have liked to see. But it's
No, I'm telling you how I represent the message in OCaml, given some arbitrary format defined by the person providing the data. So somebody is sending me this data, probably an exchange in this particular example, and they've told me what the protocol is, and I'm saying like, I have to parse this thing.
It looks like you're sort of pattern matching against what you think it should look like, right? Is that what you're saying?
Right, I read the spec and they're like, we have like 4 message types and there are these, and then I like write down a corresponding type in OCaml. But the whole point of this is that I can't assume that they'll like use the same, in fact they will never use the same memory layout OCaml does. So it'll never like be possible to represent it using this like direct OCaml form. So what I instead do is I just leave the message as a buffer and provide like accessors onto that buffer that like know based on the protocol. I mean, I can just show you, I have the code right here.
I understand that, but that will be true regardless of what language you're programming in.
Yes.
Right? I mean, even if it was C++, the message comes off, you will have to translate it into your internal format for the message, whatever format you choose.
Oh, but the point is I don't do that. I don't translate it.
So I'm not sure I understood the problem.
Yeah.
It creates accessor functions in OCaml, talks to those, they fetch the appropriate chunk of information out of the buffer. That's what I'm guessing.
Yes.
But that can be arbitrarily complex depending upon what the input format was.
Okay.
I think the issue is that the argument we have to figure out we're trying to minimize copying.
So it's like a tag in the buffer that you get, right?
Yep. Right, so that like one of the things.
The first thing you see is this is a whatever, and then that.
Yeah, if you're lucky, it's the first thing. But yeah.
In an ideal time.
Yes. Sorry. You had a question.
Why is it more efficient to parse into a type of message than to parse into a whole message type? Or parse into a type of message and then get all the components?
Sure. Because like, okay. So I can give you a kind of cheap answer, which is like, this clearly allocates.
The one on the left doesn't have to.
And the one on the left does not allocate at all, ever. I think this answer is a little bit cheap because that doesn't really explain why this is better than like if I had some extra copying in here, but like the extra copying wouldn't really help me. So, yeah. But like if you want to construct, I mean, just the way OCaml works is if you construct this thing, like you've allocated an object on the OCaml heap, and you're going to run into the garbage collector doing bad things to you, and also just like, yeah.
This problem is specific to OCaml, because if I will do this with C, I can just read the buffer and compare, and then I don't need to allocate in that case as well.
Sure. I mean, I'm not saying like, right. So I'm trying to build, like I like working in OCaml, right? I like working with this type. I don't like working in like with direct raw buffers like I would have to in C. Like, so I would like to construct a world in OCaml where I still don't allocate this type, but I get like as close as possible to working as if I had allocated it.
I mean, also you're providing a type-safe interface to the JDT. It's not like
Yeah.
in the buffer where you can just mess up.
Exactly. Right. So the previous interface I had is more like the C thing, right? Like you can just call any of these functions on any buffer and like, who knows? Here, what we do is we construct a JDT for the message type itself. And then when you get the message type out of the buffer, you get some particular message type. Then you can construct a T, and you have to say what the message type is. And if you lie, this is unsafe. So there is a wrinkle here. But once you've done that, everything after that is safe. You have, yeah.
Oh, just a little question, but the model in OCaml, is it like a type class in Haskell?
A module is like an instance of a type class in Haskell. And the signature of a module is like a type class. But that's sort of not a direct, I mean, I'm just basically citing modular type classes, the paper, to make that claim. But I just like think of it as like a library, and I'm showing you, the fact that it says like :sig here means I'm showing you the interface to this library. And it like defines some like types and values and stuff.
So that trusted content type array, which instantiate with the type A, B, and the message, that's the moment of your YOLI cast.
Yep.
After that, you're in a well-typed world of
Yes.
your financial.
Right, so you read the message off the wire, you check its message type, you call of IOBuff, you say, you give it the message type you got from here, and like otherwise bad things happen. But as long as like that part of the code is correct, everything else is fine. So now we can say, we can have the same accessors we had before, but they take an order added T. So they like, you can't call them in the incorrect case, basically. And that's like kind of all there is to this trick. It's also turns out to be nice because if you have even deeply nested messages, this still works. There's kind of one more thing we lost from this version, which is that as soon as we went to accessors instead of the full built-out type, we lost the ability to make sure we lost the ability to like pattern match on these records, basically. And the reason that's useful is that you can kind of, like OCaml will let you pattern match on records in a way that allows you to make sure you're catching all the cases. It's like it's not like enforced by the type system or anything that you must use all the values, but you can like write your code such that you do, and like we do write code that way. So in this version, we don't have any way to say like, make sure I use all of the symbol, price, size, and order ID, because like if I don't use one of those, I'm probably like messing something up. Like maybe I read the symbol off of the previous message, so I'm applying this information to the wrong symbol or something. What's it?
Okay, that sort of goes against that. So why don't you write a pattern matching Properties mean you don't use all the fields.
This sort of works, but I think you're just pushing the allocation somewhere else. Because at some point you need to implement those continuations, and they're gonna probably depend on like some stuff, and like, so you have to allocate a closure or something. You might be able to, there might be a way to get away with it. But also like, it kind of feels like you're programming a little bit inside out when you do that. But yeah, part of the point is no, because match will not. The difference is like if you try to construct this function, you have to not. Like you can do things to make this kind of work, but it's like you have to be super careful that creating the continuations you pass to the function doesn't allocate a closure. So to fix this like kind of last bit, other than the like trusted thing that I talked about before, we can just do this other trick where we make a record of accessors, which we can then match on and then like call all of, which is a little silly, but like the reason this like works and you can't just create the record of the data itself is that like this thing is a constant. There's just like one of them, and yeah. So cool. Any questions about this? Yeah. This defines a type T, a type alias T that is equal to order added T, where that T is this one. It's just convenient, so I don't have to say order added in every case here or here.
How do you deal with the case, for example, the integer is serialized in the layout? It has to be in the
Sorry, what?
big endian versus little endian.
Oh, you just write your parser to like read it out of the buffer correctly. Like, I mean, I have this like little example parser down here, and if you look at it, it says like, read this thing as a little endian int. Yeah, it's not very well explained that LE means little endian, but that's what that means. And you know, you can write like B here and it'll do something different. Yeah. Cool. Okay. Anything else? So I think like one way to think about this JDT trick is that here we have a structural type representing a message. And we're sad about this because we don't want to allocate the structural type. So in some sense, what we're instead doing is we're saying, we'll have a single type of all messages, but we will have some kind of like behavioral typing to distinguish the different cases. And then, so it's more like a subtyping hierarchy than like a variant. And then we use the JDT to like walk the subtypes. To like say, yes, we're in this subtype. And therefore we can do whatever's like valid there. So I think kind of thing, which is that a pretty common thing we do in systems like this is we have like a bunch of subsystems, and it kind of turns out the right way, a convenient way to structure code when you have like some big long-running system that has lots of subsystems is to model the subsystems as state machines, meaning like there's some state and you have a notion of like a transition on that state. And in particular, the way we try to do it is we try to make the transitions like be explicit OCaml objects, because that just makes writing the code easier. You could also like make a transition just be a function call on the like thing, but that doesn't work as well. And a common thing we see is that we have a bunch of slightly different handling for like data that is modeled similarly, but like the state machine has to be a different state machine. this is, so another way we use this JDT like subtyping hierarchy trick is to constrain a big state machine to some subset of that state machine, or like some subset of the transitions. So like I have an example of that here. There's a thing called in like market data called a book, which is like the representation of all of the orders on an exchange, or all of the like prices and sizes you can buy stuff at. And there's like exchanges will give you different levels of detail about the state of the exchange. So there's kind of different models of the book that you might get from different exchanges. And we call these BBO level and order. BBO stands for best bid and offer. It just means they tell you only the like best price you can buy or sell the thing for, and like how much you can buy or sell at that price. Level means they tell you for every price how much you can buy or sell at that price. And order means they tell you every single person who, they don't tell you who, but they tell you like every time somebody enters an order exactly like how much that is. So you can see like, there's like, 1,000 shares available at $30, but like maybe like 3 different people have different chunks of that size. So this is just like a simple example of what our internal data structure to represent that looks like. And I guess the interesting thing here is, this got messed up by the font size, by the thing. So like you can ask a book for like the orders to like try to buy the thing, or the orders try to, the stuff people trying to sell, and you can like give an aside like that. You can always like say, what's the best price and what's the size of that price, and you can always say like, I don't know, there's some like stuff you can do. You can always like iterate over all the price levels, and then each price level is like a particular price and all the size of that price. But it only makes sense to say what orders are at that price if like you have that information. So we can just say, well, we'll restrict ourselves to like only allowing you to query that part of the state if you're in the order case. So that's one way. Like that's showing kind of how like you constrain your view of the state based on which like case you're in, and also you can. But the other part is that you can also constrain like what transitions are allowed to happen. So we have like 7 transitions here. In a BBO book, the only transition that can happen is you can tell you like the BBO changed. You can always, or sorry, that's not the only thing, but like that's pretty much how they tell you updates. They can also tell you like, it's cleared. In any case, they can always tell you like a trade happened, but then like in an order book, they tell you about individual orders getting added and removed, and in a price book, they tell you about like individual price levels getting added and removed. Anyway, this is just like another example of the JDT thing. Yeah. Cool. Yeah.
So, do you use lambdas or partially defined functions?
Yes. What do you mean? Like, can I at all, or like in OCaml, or? Lambdas are fine. Well, like, if you define a function somewhere, that's fine. It will allocate when you measure if it depends on anything in the environment. But if it doesn't depend on anything, like if it could easily be hoisted, then it's free. Also, like if you do it, like we don't just have to never allocate. We have to not allocate like on the fast path. Like you can't allocate between like getting a message and like reacting to it. But you can totally just like allocate at the beginning of your program, for example. So sure, but like yeah, like there's some restriction to what you can do when you're trying to do this kind of stuff. So yeah, like you cannot like use the full power of lambdas. And similarly, partial application does allocate because it's like equivalent to a closure where you like close over the one argument you pass, or however.
Severe restrictions on functional programming. But, okay.
Yes, and like to be clear, this is not how we program all the time. It's how we program when we're writing these like carefully efficient, like fast systems. Like most of our programming is like in a world where we just allocate all the time and it's fine. But occasionally, like the path of code between like what happens when you like see some data from the exchange and like react to it by sending orders is like needs to be optimized as much as possible. But like, you know, we have lots of other stuff. We need to like have email work, for example. Okay, cool. So I guess like in that spirit of trying to not allocate ever, there's a terrible thing we do, which is that, well, I like talked about why allocating was bad, and part of my justification for that was like the garbage collector like causes latency spikes. So you can do a kind of obvious in retrospect thing of just like, well, just don't use the garbage collector and write C instead. You're not actually writing C, but you can like, you know, use manual memory management. And you can just do this by allocating memory outside the heap in OCaml. This kind of just works. Right, so we have a type we call like an external, like an x.t, which is like which just represents a pointer to an OCaml object living outside the heap. And so we, like doing this kind of thing is kind of unsatisfying because it's still allocation and like it's still not free, and like if you call free, like that's going to be expensive too, like even if you're not doing garbage collection. Like if you're using malloc instead, you're still like sad about allocation, I think. But it is still better in some circumstances to not get the huge latency spikes associated with the garbage collector. So like we'd prefer not to allocate at all, but occasionally we will do this intermediate thing. So I'm going to go through like an example of like one kind of data structure you might want to store outside the heap, which is like a super simple one, which is an array. You can create an array. Like we have this type of arrays stored outside the OCaml heap. This is what I meant by like an alpha x.t is like an alpha stored outside the OCaml heap. So this is a pointer to an array that is not like stored in OCaml, but it's still like an OCaml object. It's just like allocated somewhere else. So you can like create one by like calling this init function, and I'll talk about this. This is kind of the point in a second. You can like free it. You can ask length. You can like look up a value. Like kind of all the stuff you can do with a normal array, except that there's also this free function, and it won't get garbage collected unless you tell it to. But like, there's a problem here, which is that without that witness that I erased, so like this interface as written here is unsafe. Does anyone guess why? I think there's like, sure.
There's no guarantee that the data won't change from the next round.
I don't think you're necessarily wrong, but that's not what I'm trying to get at least. So it's unsafe because what happens if you stick something in here that has a reference to something in the OCaml heap in it? And then like there's no other references to that thing, and the garbage collector collects that thing that's referenced by something outside the heap, and then the thing outside the heap, like you try to like do a dereference, and you just get garbage. So that's really, really bad. It's like not just like an exception, it's like you just get incorrect behavior. Like, it's basically just undefined behavior. You can, like, arbitrarily bad things can happen. So we don't want to do that. But it turns out there's a restriction on this interface that makes it safe, which is that if the things you put in the array are just like integers, meaning like they're not objects that can have references to other things. They're just what we call immediates. So there's this notion in, I think, languages in general, but in OCaml we call them immediates, and it means like it's not a pointer. Like everything in OCaml is either a pointer to some object or just a single value. This is related to the fact that OCaml's memory model is like super uniform, so that we can like implement polymorphism without thinking too hard about it. So everything is a single word, and if the word ends in 1, it's an immediate, and if it doesn't end in 1, it's a pointer, because pointers are aligned, and this is why we have 63-bit integers. But all that is to say, there's this notion of like a thing that is just like a single value with no like references to other values. And like clearly this interface is safe. Well, maybe not clearly, but like the bug I described does not appear if you make that restriction, because you can't have a reference if it's just a single thing. But like, so, right, this might seem a little bit restrictive. Right, so we have this notion of like immediacy of a type. So we can say that a type alpha is like always immediate. So that's the restriction we make. This might seem like super restrictive. Like you can have an array of ints or like an array of bools or something, basically nothing else, and you're pretty sad, and like why would I even bother having this array? Because like maybe it's like useful in some cases, but it's pretty limited. But the trick is, if we look at the interface to ext as well, you'll notice that ext is in fact always immediate. Because, so you can actually store like, this amounts to saying like, it's fine to store stuff outside the OCaml heap as long as the stuff it points to is also outside the OCaml heap. Right. So I think but the thing that's cool here that OCaml let us guess is that this is not like a thing that means anything in OCaml. We made it up. We like made it up with knowledge of how OCaml happens to work, like, and happens to be implemented, but like we just made it up. It's not like it's a built-in thing to the language. So I guess just like the point here is we can create this type of like proofs of some fact about some other type alpha and like pass them around and stuff, and be able to get safety on some like low-level operations that we couldn't necessarily otherwise get. And it's like, once again, there's like a little bit of a catch, like in the first example, which is that, of course, if you like create this wrong for a particular type, you'll be sad. So what we do to get around that is we use a little bit of like type generation. So first of all, an x.t is actually just an int. But like, and I'm showing why like x.t is immediate always, but like you can also do this for lots of other types like bool and int and stuff. So we have some code generation that tells us what the like actual structure of the type is, and then we have like a function that takes that, looks at that structure and like raises an exception if it's not immediate, and otherwise returns the witness. And so you can like lie here, but as long as you don't lie when you first create the type, you don't kind of need to know the type's implementation. You can have an abstract type where you have these witnesses, and you can pass them around and like know kind of arbitrarily interesting facts, as long as you define the, like, there's some predicate here, like, and as long as you define this predicate correctly, and by define I mean like write it down when it's true, you can pass around and use it in lots of other code. I think that this is like a thing we actually do a lot, just having these kind of like phantom type where you just have this type that is kind of just a proof, and it doesn't depend on its argument at all, but like, oh, sorry, but constructing it does. So, yeah, I think that's all I have to say about that. Also, this follow thing just is like some unrelated stuff about how you actually implement like X. This is notably an unsafe function, but there are certain circumstances as well. But that's kind of tangential to this talk. And it turns out like array is not the only thing we have. We can like create pools of all sorts of values and like do malloc-like things, and except we tend to like group objects of the same type together so that we can. It just makes your malloc implementation a lot simpler, and you can like delete and create chunks all at once, and it's like it's nice. I think like the other reason this is like this is not so just like devolving into a crappy allocatey world is that because once we're doing manual memory management, we can tailor our manual memory management model to whatever program we happen to be writing at the time, and we can like get a lot of efficiency bonuses out of that. But like we hate doing unsafe things, and like especially really scary ones where you can like just get garbage. So we want to be really careful about that, and this ability to just like construct predicates like this is useful.
Is it unsafe because now you can forget to code free?
Sure, but then you just get a memory leak.
Yeah.
And you can free stuff and then use after free, and that's also unsafe. But it's like less unsafe.
Can you simulate somehow destructors like in C++ and the GART?
OCaml has like the GART. You can install a like thing that happens when the garbage collector collects something,
Yeah,
like a.
It's not you need like deterministic destruction.
Where you, what do you mean?
I mean,
Sure,
when
but like.
you can have like finalizer that goes when the garbage removes your memory.
Yeah, we can have that.
It's undeterministic
Because the garbage collector could like wait forever to run, sure. So what would you prefer we have?
the question is how we can simulate deterministic destruction.
Like what would make it deterministic? It happens exactly when it goes out of scope. It happens like,
Yeah, like when
oh, sure.
goes out.
I mean, OCaml doesn't give us any way to do anything like that. You can like create a destroy function or a free function and like call it, and you can do this in general. Like there's a case in incremental where, which is a library that we built based on work by like Amudakar and his colleagues on self-adjusting computation, that like allows you to do pretty easy like construction of incremental computations. And one interesting thing that happens in that library is like the garbage collector is actually really slow to collect like dead nodes in your like incremental computation graph. And so we just provide a function that's like, just unallocate this thing for me. And you just do it early, tell the garbage collector, like, and then the garbage collector will come up, and, you know, it'll already be gone. And we can do that kind of thing, but it's still like not super satisfying because it's like still super manual. You have to like say, like, you can write code to do things, but there's nothing gonna like happen for you. in some deterministic way, which, sure, probably sad. But like, I probably want that if it existed. Yeah, so I think like overall, part of the point here is like things that we've found to be really useful are like ways to access memory, access some data like in a nice type-safe way, but that like respects whatever layout of the memory happens to be like given to us by somebody else. Like, you know, normally the way this works is like we have our we have some representation of an object in OCaml, and OCaml just like picks the memory layout for that thing. So like the thing that I would like to have more of in OCaml, and I'm not saying that this doesn't exist in other languages, is like ways to have the memory model first, and then like just tell the language how that corresponds to the type, or at least like have a type that corresponds to any memory or something like this. So more stuff like that would be nice. We have this like way of doing it with JDTs, but you know, doesn't solve all problems. Another thing that I think like we want more of is like the ability to kind of prove more facts, especially facts we made up, predicates we made up by you know, just doing manual proofs. Like I don't care if this is, like if this was built into the language, probably like OCaml would infer whether the thing was immediate and you would never like need to write it down, but like I don't actually care about that. I just want the ability to say it at all, for example. So maybe that's suggesting I should be writing like Idris or something, but anyway, I think that's pretty much all I have to say. Are there any questions?
So I'm just curious, like, at some point you must have realized you had to do this. So what kind of performance did you see when you said, like, oh, let me remove it from the buffers? Or what was the change when you implemented your own external key?
Right. So I think we realized about 5 or so years ago that allocation is really, really bad. And a lot of that is driven by this. And also like, but I don't have like, you know, numbers for you. But I mean, as an example, like, we have some trading systems that like are old and legacy and like allocate or allocatey. They're probably like badly written in the other ways as well. And like their processing time is maybe like on the order of milliseconds or hundreds of milliseconds even in the worst case. And like an interesting point here is we care about the worst case latency, not just the latency, because the case where the events are interesting is exactly the case where the market is busy. So like you care about what your latency is in the case where you're like busiest, not in like the average case or anything. So these things have worst case latencies of like hundreds of milliseconds. I think like our fastest trading systems are better than 50 microseconds, without saying more than that.
Was that the target, or is that what you got? In other words, did you go in saying, well, we've got to be able to respond to an interesting event, the environment is really loaded, and it's got 50 microseconds, or is that just what has turned out?
So I didn't do this work, but we've done some work where we've tried to like measure how good it would be to be like to beat certain like there's a certain extent to which it's just better to be like a little bit faster in general, like kind of continuously. And there's also points at which there's like a jump discontinuity because you've suddenly gotten faster than someone. And we sometimes try to measure that, but it's really, really hard. So, like, first of all, 50 mics is not the actual number. It's faster than that. But I think like there were some, I believe that at the time there were some targets like around that point of like tens of mics where like being that fast was important. But there are other targets that are like in the measured in nanoseconds or something. Probably not single digit, but and like, you know, we're kind of constantly trying to get better at this in various ways. Yeah, I mean, I think to do this you need just, well, we are co-located with the exchanges, but yeah, I mean, and like at some point to do the very fastest stuff you have to like use hardware, but there's also trade-offs. Like a lot of what we make money on is like actually understanding what the price of a thing should be. So a lot of our trading systems are like kind of slow but like have really good understandings of what's going on in the market. And you can build faster ones that are dumber, but like, you know, and that you run different strategies on these different systems. But so like nobody can do like the fanciest systems in, you know, a few nanoseconds, because like you just like, if you have to do a multiply, you like, too bad, you've already lost, right? Like, so like anytime you're trying to do any interesting math, like you're sad in that case, which is like obviously pretty restrictive. But you know, move up to microseconds and suddenly you can do multiplies and you're fine. So I think like part of, I guess I'm just saying like the type of thing you do at different speeds is different. So like the hardware will be valuable, but like we still won't be able to run the fanciest, like most complicated systems on it.
I think the technique you presented here is called zero copy parsing. And just want to know that this also have many practical usage for networking and web application, because
That makes sense.
they want to pass the data to very fast.
Yep.
Things like HTTP headers and JSON. And so I see that Haskell has a zero copy parser library called OPLSS, and OCaml has a counterpart called Angstrom. Have you tried any of those?
Angstrom is actually written by a Jane Street employee. But we don't use it. But for all of these like protocol parsers that we're using here, we just have like a library that code generates the code for them, basically. We call it ProtoGen. But I've seen Angstrom, and like I think it has, you know, I think it's useful, but we happen to like not use it for this particular thing. Yeah.
Is the format the data comes in on like a reasonable format, or is it archaic in some way, or does it like update often?
It depends on the exchange. It does update often. I mean, my job in particular is often to react to the fact that it updates a lot. It updates a lot. There's lots of different exchanges, so there's lots of different protocols. Some of them are better and some of them are worse. Like, kind of more of the like advanced technological exchanges will, you know, and especially the bigger ones will like have thought about this for several years and have a protocol that's like pretty settled and like makes sense, and you know. But like sometimes they'll do things that make it really hard to parse efficiently, and you're like kind of annoyed by this, but like mostly because of the writing of the code rather than the actual speed problems. Yeah, so like ideally lots of people copy the people who figured out how to do it well, but part of the problem is the actual model of the data is different on different exchanges because they have different market structures, which is like a buzzword that basically means, or like, you know, industry terminology that basically means like what is the state machine they have in the exchange. And like the data they're giving you is just kind of like a view on that state. So because those state machines can just be legitimately different, sometimes they have to make up their own protocol, but often they do this like badly. And like, you know, I think that it's hard, yeah.
The problem for performance that there is no comparison support?
No, because like I said, like what we care about is latency, not throughput. And the way we get throughput is we just parallelize. And it's very, very easy to parallelize the stuff we do. So, because like the way it works is like there's a bunch of symbols that you're trying to trade. You know, you probably have a strategy around each symbol that's like correlates with other symbols. So you might need like data for a bunch of products on one to be together. But in general, you can just like take all the products that exist, like divide by n, and like write n processes. So we just do process level parallelism, and it's like super simple, and that just solves all of our throughput problems.
So because you know in advance what the sense of you can
Yeah, exactly. I mean, you can like measure like how much people trade various things to like do this in a way that's like nice. And so like if you just divide by symbols, like I said, that's not quite good enough, but you can like measure how much volume there is on each one and stuff like this. And just like, it's nice to be able to avoid the overhead of concurrency. Like it, you know, because like there is overhead to communication. If we had to do it, then maybe we'd be sad, but we just don't have to. They're theoretically working on it though. It's the next thing, supposedly. Okay. Anybody else?
So when you say you don't copy things, what if you need to use that value again and again? Do you directly
I mean, yeah, like the individual program like processing the particular case, like often you don't, but if you do, you probably want to like save the specific subset of the message that you care about rather than like the whole thing. But yeah, that exists, like that happens.
So basically, you can extract from the buffer, like network buffer, and directly put in like non-ML stuff. I mean, outside the heap.
No, you just copy, like you just like have a ref somewhere that's like pre-allocated that says like, ah, yes, this is like the value I need to know for the future, and then you just like write the one you care about in. And if you like need an arbitrarily long list of these, then you need a queue, and maybe you're sad, but like probably you don't most of the time.